A very good morning to all of you. Till now we have been discussing electrostatics and magnetostatics, and then we discussed laws of dynamics, electrodynamics, and then finally we introduced the concept of Maxwell's equations and electromagnetic waves. So, in all these lectures we have tried to understand the basic concepts through the various laws, Gauss's law, Ampere's law, Faraday's laws of induction and so on, and try to understand how charges and electric currents behave, what are the forces acting on them, and some applications. We have discussed a lot of concepts. Now, what I want to do is I would like to discuss some problems in the area of electrostatics and magnetostatics and also the waves, so that we understand better how to utilize some of the concepts that we have developed in the course. During the course of lectures, we have also discussed some problems, but today I would like to discuss some additional problems which will help you to understand some of the concepts that we have developed. Problem solving is a very important aspect of physics, and the more problems you solve using various concepts that has been developed in your career, the more you will understand the concepts themselves and their applications. So, I have picked up some problems in the field of electrostatics today, which I would like to discuss. And so, let us start with the first problem. So, the first thing that we have seen that electrostatic fields are fields produced by charges in rest, and those fields satisfy certain kinds of equations. We have seen Coulomb's law, we have seen Gauss's law and so on. Now, the first question which I want to look at is it possible to have an electrostatic field of the form E is equal to E naught x j cap. So, that is a vector field with magnitude E naught, and it depends on position x, and it is directed along the y axis j cap. So, the question is, this is a vector field, and can this vector field represent an electrostatic field? Now, we have discussed electrostatics in great depth. So, what we know is all electrostatic fields satisfy the following equation: integral E dot dl is equal to 0. If you take the electrostatic field and do a line integral over a closed path, then you will find it to be 0, because these are conservative fields and electrostatic fields satisfy this equation. So, if this field is to represent an electrostatic field, it must satisfy this equation. That means, if I take any closed path, integral E dot dl must be equal to 0. So, I am at liberty to choose any particular closed path. So, I would like to choose a closed path for which this integral can be analytically solved. If I take a very complex path, I may have difficulty in solving the equation integral, but I would like to take a simplified path. So, the path which I like to take is the following. So, let me draw the x and y axis here. This is x axis, this is y axis. So, I take a path like this, I take a path in this form. So, I go from here, I start from the origin and complete one complete rectangular square path here. So, let me assume that this is a rectangular path, here is A, this is B. So, let me call this A, B, C and D. So, electrostatic fields must satisfy this equation E dot dl is equal to 0. So, what I would like to do is to use this electrostatic field, this vector field in this equation, and find out whether this particular field integral E dot dl over this path A, B, C, D, A is 0. So, integral E dot dl is actually equal to A to B E dot dl plus B to C E dot dl plus C to D E dot dl plus integral D to A E dot dl. It is a complete closed path integration. Now, what is integral a to b E dot dl? Is equal to integral. Now, E is nothing but E naught x j dot. Now, dl is, I am integrating from a to b, that means dl must be along the x axis. So, dl is nothing but I cap dx, and because j cap dot I cap is 0, this is equal to 0. Integral a dot b a to b integral E dot dl is equal to 0. So, similarly, you can show that integral c to d E dot dl is also 0, because the electric field is pointing along the y axis and the integration is along the x axis, along the x direction. So, these integrals are 0. Now, what about the remaining two? Integral b to c E dot dl is equal to, now b and c are on the same value of x and electric field depends only on x, and the value of x at this in this line is x is equal to a. So, this is equal to b to c. So, b is x is equal to 0 and c is x is equal to b E naught. Now, the value of x here is a, because electric field as you can see here is E naught x j, on this line x is equal to a. So, E naught a j cap dot j cap dy, which is equal to integral 0 to b E naught a dy, and E naught and a are constant. So, this is nothing but E naught a b, E naught times a b. Now, what about the final integral, one which is d to a, integral d to a E dot dl is equal to, now this is a line which is on the x is equal to 0 line here, and at x is equal to 0, as you can see the electric field itself is 0. So, this integral is also equal to 0. So, what I have been able to show is integral E dot dl for this field, vector field, is nothing but E naught times a b, and this is not equal to 0. So, E is equal to E naught x j cap cannot represent an electrostatic field. So, please remember, it is not all vector fields will represent, can represent electrostatic fields, only those vector fields for which integral E dot dl over the closed path is equal to 0 will represent electrostatic fields. So, the way to check is, given a vector field like this, I take a suitable path of integration, and if I find this integral to be non-zero, that means this vector field cannot represent an electrostatic field. Now, I will here leave a question to you, how about a vector field, how about the following field? E is equal to E naught x I cap. Can this represent an electrostatic field? So, please work out in a similar fashion like we have done and find out whether this particular field can represent an electrostatic field. You follow the same procedure as we have done and you will be able to find out whether this can represent an electrostatic field. Now, let me look at a second question. Now, remember, electric fields and potentials are related to each other. So, I given the following electrostatic potential calculate the corresponding electric field. So, potential is V is equal to V naught for r is equal to square root of x square plus y square plus z square less than a is equal to v naught a by square root of x square plus y square plus z square for r is equal to square root of x square plus y square plus z square greater than a. So, what is given is it is a spherical distribution. The potential is V naught within this sphere of radius a, and outside the potential decreases as 1 by r as you move away from the center. The question is, what is the corresponding electric field distribution? Now, to solve this problem, we have during the course of lectures we have derived the following equation. The x component of electric field is related to potential through this equation. The y component is minus del v by del y, and the z component is minus del v by del z. Remember, I am using partial derivatives because potential v is a function of x, y and z, all three coordinates, and this is a differential with respect to x keeping y and z constant, differential with respect to y keeping x and z constant, differential with respect to z keeping x and y constant. So, first for r less than a, the potential is constant. So, we will have E x is equal to del v by del x minus del v by del x is equal to 0. Similarly, E y is equal to minus del v by del y is equal to 0, and E z is equal to minus del v by del z is equal to 0. So, within this sphere of radius a, because the potential is constant, there is no electric field within the sphere of radius a. Now, what about for r greater than a outside the sphere? Let us calculate the three components. So, E x is equal to minus del v by del x, which is equal to minus del by del x of look at the potential here. So, V naught a by square root of x square plus y square plus z square, which is equal to minus V naught a del by del x of 1 by square root of x square plus y square plus z square. This is a simple differential. So, minus V naught a into minus half 1 by x square plus y square plus z square raised to the power 3 by 2 into 2 x. Differentiating this with respect to x gives me minus half divided by x square plus y square plus z square raised by 3 by 2 into 2 x, and this is nothing but V naught a x by x square plus y square plus z square raised to power 3 by 2, which is nothing but V naught a x by r cube. R is square root of x square plus y square plus z square. So, this is nothing but r cube. So, E x happens to be V naught a x by r cube. Now, if you look at this equation here, the potential is symmetric with respect to x, y and z. So, just by symmetry I can immediately write down the values of E y and E z. So, E y will be equal to minus del v by del y, which is equal to V naught a by r cube, and E z will be equal to minus del v by del z, which is equal to V naught a z by r cube. So, we have E x, E y and E z. E x is this, E y is this and E z is this. So, I can write the total electric field E is equal to E x I cap plus E y j cap plus E z k cap, which is equal to V naught a by r cube into x I cap plus y j cap plus z k cap, which is nothing but V naught a r vector by r cube. And here r vector is nothing but x I cap plus y j cap plus z k cap. So, the electric field, this potential distribution which I have written here, this potential distribution corresponds to an electric field given by E is equal to 0 within the. So, E is 0 within the sphere, and outside the sphere the electric field goes as V naught A r vector by r cube. Now, please note one interesting aspect here, that the electric field was 0 inside the sphere and is non-zero outside the sphere, and it is discontinuous. So, at r is equal to A, if you come from within the sphere the electric field is 0, if you come from outside the sphere the electric field has a finite value. So, the electric field here at this interface is not continuous. The potential distribution is continuous, but electric field distribution is not continuous. So, it is possible in situations that the electric field may not be continuous, and in an advanced course you will understand this better, because it so happens that the normal component of electric field will not be continuous across an interface like this. So, that is the second problem we have discussed. Now, I want to look at another problem, which is suppose I have a pair of charges plus 2q and minus 2q are placed at a separation d as shown. The point P is midway between the two charges. What will be the value of integral P to Q E dot dl along a semicircular path of radius d by 2. So, we are given two charges, there is a minus 2q here and a plus 2q here, there is a point P midway here, and there is a path which I choose is this one, this is q and this radius is d by 2 and this distance is d. So, the question is, what is the integral E dot dl from P to Q along this semicircular path? Now, please remember that we have seen that potential, we can define a potential for an electrostatic field, and potential gives nothing but the work done in moving a charge from one point to another point, that is the potential difference. So, I can use this concept to immediately calculate the value of integral E dot dl from P to Q irrespective of the path taken actually. So, we have essentially integral P to Q E dot dl is equal to potential at P minus potential at Q. Integral E dot dl from P to Q is simply the difference in potential between P and Q irrespective of the path taken. So, whether I take a semicircular path here or another path here, as long as my starting point is P and ending point is Q, the value of integral E dot dl is nothing but V p minus V q. Now, what is V p? The potential at P. Now, this point P is midway between these two charges. So, potential you know is charge which is 2 q divided by 4 pi epsilon 0 into distance of the point P from the charge plus 2 q, which is nothing but d by 2. And then you also have a potential here because of the second charge, which is minus 2 q by 4 pi epsilon 0 into again d by 2. Distance from here to here is d by 2, distance from here to here is d by 2, and so that is 0. So, the potential at this point is 0, it is equidistant from two charges, equal charges plus q, 2 q and minus 2 q. What about the potential at Q? So, q is at a distance d by 2 from plus 2 q and 3 d by 2 from charge minus 2 q. So, the potential is 2 q by 4 pi epsilon 0 into d by 2 minus 2 q by 4 pi epsilon 0 into 3 d by 2, which you can simplify and show this is 2 q by 3 pi epsilon 0 d. So, integral p to q E dot d l is equal to V p minus V q, which is equal to minus 2 q by 3 pi epsilon 0 d. So, please remember, I could have made the problem more complicated by calculating the electric field as a function of position and actually substituting the electric field inside and integrating. That would have made my life very difficult, but because integral E dot d l is nothing but the potential difference between the points p and q, I can very quickly solve this problem and get the value of integral E dot d l from p to q as this. Now I leave it as an exercise to you to please think what is the significance of this minus sign here. Integral p to q E dot d l is minus 2 q by 3 pi epsilon 0 d. So, please give a thought as to what is the significance of the minus sign in this equation and try to analyze why there is a minus sign. Okay, now let me look at another problem. Consider an electrostatic field given by E is equal to 20 I cap plus 30 j cap volts per meter. Calculate the potential difference between the origin and a point P with coordinates x is equal to 2 meters, y is equal to 2 meters, z is equal to 2 meters. So, that is the constant electric field, as you can see 20 I cap plus 30 j cap, and I want to find out the potential difference between 2 points. One is the origin and another is a point x is equal to 2 meters, y is equal to 2 meters, z is equal to 2 meters. So, let me draw the figure here. So, x, y, z. So, this is 2 meters here, then 2 meters here and 2 meters here. So, this is the point. So, I have to calculate the work done, a potential difference between this point and this point, and the potential is actually nothing but minus integral. Suppose I call this A, B, C and D, A to D along the path, along this path shown E dot d l. I can just choose any path, but I would like to choose this path for simplicity. So, this actually consists of 3 parts minus A to B E dot d l. Now, if I go from A to B, what is d l? I cap d x minus integral B to C E dot j cap d y plus minus C to D E dot k cap d z. This is d l for path A B, this is d l for path B C, and that is d l for path C D. So, this is equal to minus integral. Now, A to B is 0, x goes from 0 to 2, because this has coordinates 2 meters, 2 meters, 2 meters, and E is given by 20 I plus 30 j. So, this is nothing but 20 dx minus b to c, value of b at y at b is 0 and c is 2 meters and E dot j is 30 dy minus, now electric field has no component along k cap. So, E dot k cap is 0, that is 0, and this is nothing but minus 40 minus 60, which is equal to minus 100 volts. So, that is the potential difference between A and D, that between the origin and this point D, which is minus 100 volts. So, what I have essentially done is done an integration E dot dl by taking an appropriate path. You can take any path from A to D and you can do the integration, and in principle it's good to choose a path for which the integral can be analytically evaluated easily. Now, let me look at another problem in which there are forces. So, 2 point charges of equal mass m and carrying equal charges q are suspended from a common point. By two strings having negligible mass and of length L. Obtain an expression relating q and theta at equilibrium Now, let me show theta here. So, this is one charge which is here. So, this is q, and this is theta. So, because of repulsion, electrostatic repulsion, the two charges move away and they are connected to a string. So, they are in equilibrium position like this. Now, the question is, what is the relationship between q and theta? So, to solve this, I must write down the force balance equations. So, let me draw the figure again here. So, you have one charge here, another charge here, that is the normal, this is theta. So, there is a force mg acting here, there is an electrostatic repulsive force acting here, and there is a tension on the string. And if I draw a perpendicular here, this is also theta. So, I can immediately write at equilibrium that all the forces must balance each other. So, if I look at the vertical component, I have T cos theta is equal to mg. T cos theta is the component of the tension in this direction. So, that must balance mg, and the component along the horizontal direction must balance the electrostatic repulsion. So, T sin theta is equal to F e, which is equal to q square by 4 pi epsilon 0 into this distance square. And what is this distance? This length is L. So, this is L sin theta. So, the total distance is 2 L sin theta. So, 2 L sin theta whole square, which is equal to q square by 16 pi epsilon 0 L square sin square theta. So, I have two equations. I can eliminate the tension T from these two equations by dividing the second equation by the first equation, and I get tan theta is equal to. So, I have, so if I divide T sin theta by T cos theta, on the left hand side I get tan theta, on the right hand side I will get the following equation, q square by 16 pi epsilon 0 L square sin square theta into 1 by mg. So, q square is equal to 16 pi epsilon 0 L square mg sin square theta tan theta. So, if you know the charge that is put on these particles of mass m, you can actually find out the angle theta at which the equilibrium position will be obtained. So, what is essentially happening is I have to write the force balance equation. There is a mass weight which is acting downwards, there is an electrostatic repulsion acting sideways here, and there is a tension in the string. So, I can actually write down the force equations and eliminate the tension and get a solution connecting the charges and the angles. Now, we had done discussed about electric fields in matter. So, in that connection let me take a problem. So, free charge is embedded in a linear dielectric sphere of dielectric constant K1 and radius r. The free charge density rho f is equal to alpha times r, where alpha is a constant and r is the distance from the center. This sphere is surrounded by another spherical shell of radii r and 2r and of dielectric constant K2. Calculate the electric field and the displacement. Vector D everywhere. So, the problem is essentially the following. So, I have a sphere of radius r, dielectric constant K1 surrounded by another sphere, a spherical shell between r and 2r. This is dielectric constant K2. Here there is a free charge density is equal to alpha r in this. So, the problem is to calculate the electric field and the displacement vector. Now, remember in when we discussed Gauss's law in dielectrics, we obtained a form of very important form of Gauss's law, which is integral d dot dA is equal to qf enclosed. That is integral d dot dA, d is the displacement vector, d was defined as d is equal to epsilon 0 E plus p, p was the polarization vector, and d dot dA is equal to free charge enclosed by that surface. Now, the advantage of this formulation as we saw at that time is I do not need to know the presence or absence of bound charges anywhere, it is only the free charges which I need to know which will decide my displacement vector d. Now, because of the symmetry of this problem, again d vector, E vector and P vector will be along radial direction. Everywhere, and will only depend on r, where small r is the distance of a point from the origin. Because of spherical symmetry, D, E and P will all be radial in the radially oriented direction and will only depend on small r. So, I can use this immediately to solve the problem. So, for example, for 0 less than r less than capital R, that is within the inner sphere of radius capital R. So, I have this is my sphere of radius r. So, I take a sphere of radius small r. So, and I integrate over this. So, integral d dot d a is equal to q free enclosed. Now, because displacement vector is radial and does not depend on the position on the sphere. So, the left hand side will be simply d into 4 pi r square, and the free charge enclosed I have to calculate because the free charge density is not constant. So, this will be 0 to r alpha r into 4 pi r square dr. So, 4 pi r square dr is the elemental area, elemental volume lying between a radius small r and a radius small r plus small dr. So, that spherical shell will contain a charge so much, that is the volume multiplied by the charge density, and if I integrate this I will get all the charge lying between 0 and r. So, this is nothing but 4 pi alpha integral r q dr 0 to r, which is equal to pi alpha r is per 4. So, d vector d is equal to alpha by 4 r square r cap. This is for 0 less than r less than r. And I know the relationship between d and E vector. So, E vector is equal to d vector by epsilon 0 times dielectric constant. So, this is nothing but alpha r square by 4 epsilon 0 k 1 into r cap. So, that is the electric field, and in fact, you can calculate the polarization also. P is equal to d minus epsilon 0 E, which is equal to epsilon 0 into k 1 minus 1 into E, which is equal to k 1 minus 1 divided by 4 k 1 alpha r square r cap. That is a polarization vector. So, what I have done is I have used Gauss's law and I have used symmetry arguments to find out the displacement vector within the sphere, and also from there the electric field vector and the polarization. Now, I can similarly do for the space between the two dielectrics. That means, in this spherical shell between small r this capital R and capital 2 R, again. So, for r greater than r but less than 2 r, again I will use this formula d dot d a is equal to q f enclosed. So, I get 4 pi r square into d is equal to, now please remember the free charge is enclosed only within this inner sphere. So, I will get integral 0 to capital R only alpha r 4 pi r square dr, which is nothing but pi alpha r 4. So, I can write an expression immediately d vector is equal to alpha by 4 r 4 by r square r cap, and E vector is equal to d vector by epsilon 0 now k 2 the dielectric constant. So, this is alpha r 4 by 4 epsilon 0 K 2 r square r cap. That is the electric field, and you can write down expression for immediate depolarization, which is d minus epsilon 0 E. So, what I have done essentially is, for this problem there are dielectrics, and I have been able to solve I have been able to obtain the electric field and displacement vector. Now, for r greater than 2 r, again I will apply the same formula, d dot d a is equal to q f enclosed, and I will get 2 pi r square, sorry 4 pi r square d is equal to, now the free charge enclosed is still pi alpha r raised power 4. So, d vector comes out to be equal to alpha by 4 r 4 by r square into r cap, that is the d vector, and E vector, because it is free space, d vector by epsilon 0, which is equal to alpha by 4 epsilon 0 r 4 by r square r cap, that is the electric field, and P will be equal to d minus epsilon 0 E. Please find out what is the value of polarization outside in the region beyond small r is greater than 2 r. Okay. So, find out the polarization in that region and check for yourself and try to conceptually understand why you get a certain value of polarization. Okay. Now, I want to look at another problem, which is the following. A point charge q is placed at a distance a by 2 above the center of a horizontal square surface of edge A. The electrostatic flux through the square surface will be, now let me give you 4 choices: q by epsilon 0, q by 4 epsilon 0, q by 6 epsilon 0 and 0. So, the problem is essentially I have a flat square surface of side A, and I have kept a charge q at a distance a by 2 from the surface along the central line. The question is, what is the flux passing through this surface because of this point charge? Now, obviously, you can do an integration E dot dA to calculate the flux, but that is much more complicated. I can very quickly solve the problem by understanding that because I have this surface here, let me construct a complete cube around this, and the charge is at the center of this cube, because this is side A, this is side A, and this is side A, and this height is a by 2. So, the charge is placed at the center of a cube of side A, and because it is a point charge, the electric flux is uniform. It does not depend on the angle, it depends only on the position. So, and these 6 surfaces, there are 6 surfaces now of the cube which are surrounding this, and they are equidistant from the point source. So, the total flux emitted by the total flux coming out of the charge q is q by epsilon 0. The total flux and out of this 1/6 must be passing to this surface, 1/6 each must be passing to each of these surfaces, because they are all equidistant from the point charge. So, the correct answer to this problem is the answer C here, which is q by 6 epsilon 0. So, in many of these problems, as you can see here, I should be able to use symmetry arguments to solve the problem very quickly, because that can help me to resolve the problems very easily. Now, let me give you another problem here. Consider a set of 2 point charges q1 and q2 and a uniformly charged sphere of radius r with uniform volume charge density rho. Obtain the values of A integral E dot d A over the closed surface S B integral E dot d L over curve C, C for what value of rho will integral E dot d A over S will vanish, and D draw a closed surface through which integral E dot d A will be independent of rho. So, the figure is as follows. So, you have a spherical charge distribution of radius r, and you have another point charge here q2 and a point charge q1. So, that is my surface, this is the closed surface S, and that is my contour C. So, the first thing is, what is the value of integral E dot d A over the closed surface S? So, we know from Gauss's law integral E dot d A is equal to charge enclosed by epsilon 0. So, integral E dot d A over the surface S is the charge enclosed by the surface S divided by epsilon 0. The charge enclosed by the surface S has, now these are two charges, the charge q2 is enclosed by surface S, and the entire charge contained in the sphere is also enclosed by surface S. So, this is nothing but 1 by epsilon 0 times q2 plus the total charge of this sphere, because the sphere is uniformly charged, 4 pi by 3 r cube rho. That must be the value of the electric flux, electrostatic flux crossing the surface S. Now, what about integral E dot d L over curve C? Please remember, no matter what path you take, for an electrostatic field, integral E dot dl over a closed path is always 0. So, same thing will happen for the curve C, the contour C, integral E dot dl will be simply 0. Now, the next question is, for what value of rho will integral E dot dA over S vanish? So, I must put this equal to 0 and I can get the charge density required to make out that the total flux crossing the surface S becomes 0. All that you need is that the charge contained in the sphere must be equal and opposite to the charge q2. So, if q2 is positive, I need to have negative charges in the sphere. If q2 is negative, I need to have positive charges in the sphere. So, the total charge enclosed by the surface S divided by epsilon 0 is the flux, and if the total charge is 0, the net flux becomes 0. And then you have to draw a closed surface through which integral E dot dA will be independent of rho. So, I leave this problem to you. Please think of a surface in this figure where you can draw such that integral E dot dA will become independent of the charge density on the sphere. Another interesting question that we must understand is, let me look at the following: the relation d is equal to epsilon 0 E plus P holds good only in free space B, only inside a dielectric C, only outside a dielectric and D everywhere in space. So, we had introduced this equation relating electric field and polarization to displacement vector D vector, and the question is whether this equation is valid everywhere or only in certain regions. So, please think about this and try to analyze this problem and try to understand where this particular relationship will be valid. Now, I want to look at the final problem here. So, two non-conducting spheres solid spheres of radii r and 2r having uniform volume charge densities rho 1 and rho 2 respectively touch each other. The net electric field at a distance 2r from the center of the smaller sphere along the line joining the centers is 0. Obtain rho 1 by rho 2. Okay, so let me draw the figure. So, you have a bigger sphere and a smaller sphere. This is radius 2r, this is radius r. So, it is given. So, rho 1 is the charge density here, rho 2 is charge density here. So, it is given that at a distance 2r from the center of the smaller sphere, the electric field happens to be 0. So, there are and on the line joining the two centers. So, let me draw the line joining the centers. So, there is one point which is at a distance 2 r from here. So, this distance is 2 r, and there is another point here which is also at a distance 2 r from here. So, you need to calculate the total electric field at this point because of rho 1 and rho 2, and you need to calculate the electric field here because of rho 1 and rho 2. So, find out the ratio of rho 1 to rho 2 for making this electric field 0 and the ratio of rho 1 to rho 2 to make this electric field 0. So, I will give you the two solutions here. You can show that you can have rho 1 by rho 2 is equal to minus 32 by 25 to make the electric field 0 here, and to make the electric field 0 at this point, rho 1 by rho 2 is equal to minus 4. Please be careful in calculating the electric field here, although the entire sphere is charged. To calculate the electric field here, you must be careful in calculating that field inside a uniform charge distribution and use that electric field to calculate and show that there are two solutions of the problem. The electric field will be 0 here provided this ratio is minus 32 by 25, and the electric field here is 0 provided rho 1 by rho 2 is minus 4. So, today I have discussed certain problems in electrostatics. I picked up some problems which contained calculation of electric fields, calculation of displacement vector, calculation of forces and so on, and trying to calculate the flux, the potential difference, etc., to make you understand a little better. I would urge you to solve more and more problems based on the concepts developed, understand the concepts very well and use those concepts to solve problems, and that will help you to further understand the concepts and help you to solve problems. So, we will now stop here. In the next lecture, I will discuss problems containing magnetostatics and electromagnetic induction and so on. Thank you very much.